twist has
So the backward variable now is basically beta. Is the probability of being in state Si at time t and observing the partial sequence of the last observation until the t plus first observation. So this can be written as such, and again we compute this recursively with beta t, and this is now capital T, so we are at the end of the sequence, is 1, so we are definitely ending somewhere. And then, I mean, if this was 0, and we would multiply this into our probability, everything would always be 0, so that's why we started with 1 there, obviously, okay? And then, for beta t, we can calculate this through the sum overall, the transitions, the observations in each of those transitions, and then multiplying this by beta. So this is basically moving backwards through the graph. So when we're in state Si, we can go to n possible next state Sj, and each with probability Aij, so this is kind of like this part down here, and then while we're in these states, we generate the observations, and beta t plus 1 explains the observations after time t plus 1. So these are the observations, and then this explains what we have observed towards the end of the sequence. Okay, and now, so this is basically if we use this part, the betas and the alphas, we can compute the probabilities of going through this network. So if we want to learn the model parameters, we are following a new algorithm. It's called the Baum-Welch algorithm, which is derived through the expectation maximization procedure. So in this case, we seek to find a model star that maximizes the likelihood of generating a set of observations, and for this we need to define a new variable chi, or psi, the probability of being in state Si at time t and in state Sj at time t plus 1. So that's our variable here. Now it becomes clear why we needed these two alpha and beta variables. So basically, we compute everything that's happening until this point through our alpha, and everything that happens until this point through our beta, and then we just need to multiply in our transition probability and the omission probability, or the observation probability of observing this thing here, and normalize the whole process here. Okay. The Baum-Welch algorithm is a special case of the expectation maximization algorithm that you might know, and we need to learn this chi and gamma. I think I have a slide on the gamma next. Yeah, and we basically need to update our current model, or like we need to calculate this for our current model, and then compute the new parameters that further optimize the probability to observe this set of sequences. And these steps are alternating, so we do expectations, we compute the probabilities for a certain model, and then we maximize, and then we compute the expectation, and then we maximize again. And then, through the iterative process, we get to the optimal model. Okay, and the gamma here again is defined through our alpha and beta variables, which is basically the probability to be in state Si time t given an observation and a model. So this is basically this sequence here. So at time t we're in state I given our observation and model, and as I said, this can be defined through our backward and forward, where on the forward part, we have the sequence O1 to OT for the alphas, and then OT plus 1 to O capital T, where we are at the backward part, and then we normalize this again, obviously through all the possible transitions. Okay, so for the expectation step, we compute the expected values for these gammas and for these chi's. And we have some indicator variables that if we are in SI or if we are transitioning from I to J. And this is important because otherwise we would compute all of them, so we kind of just count how many times we are transitioning from SI to from state SI, and how many times we transition from SI to SJ in our present and these will be used in the maximization step. For the maximization step, we need to sum up over all these transitions and all the times that we end up in these, and our new maximum estimation for the transition probabilities are now the ratios of like how many times do we move from I to J on how many times we were in I, and then for the omission, the observation probabilities, basically the number of times that we end up in J observing a certain item in our vocabulary normalized by the number of times that we end up in this location. So this basically is the support for a certain observation given how many times we're here, and this is the support for a certain transition given the times that we end up in this location. So this is kind of the way we maximize these parameters. And now these Aij and Bj, they go into the calculation of these variables for the next expectation step, and through the iterative process we get to the optimal model. So yeah, now that we have k many observations, we can just add these sums over k here, and we get our model parameters. And for the pi's, we just look at like how many times we are in state I, given that it's time step 1 divided by the number of observations that we have in our model. Okay, so this is not too important, but just for you to have like some basic understanding of what hidden Markov models do. For the model selection, we already touched upon this a little bit, where we said, okay, so you can have like fully connected or like left to right models, where we have these different types of transitions. In this case, we have a special case where a transition from 1 to 4 isn't present, for example. So there are very different, or often different kinds of topologies that we could use for hidden Markov models, and there's no real rule to use always left to right or always fully connected, etc. So this is kind of again like a hyperparameter which you should try to optimize for and try to validate for. So like which model is the best is unclear most of the time, but you could try to like infer based off of your prior knowledge. Okay, like phonemes work like this. There's like some chord-equation part, some middle part, some end part, and you could try to find a meaningful architecture that way, or otherwise just try out different types of architectures. Yeah, these are just some additional information, and so this is, for example, a couple of phoneme level, word level, where you concatenate phonemes, and you could also kind of build sentence level hidden Markov models as such, where you have like some certain transition probabilities, or allow certain transitions or disallow some. Okay, So that's it for hidden Markov models. Are there any special questions for that? If not, we move on to conditional random fields, which are basically the discriminative version of these sequence classifier models. And just as an observation or as an outline, we're gonna talk a little bit about the logistic classifiers, feature functions, some regularization. Then there are many advanced versions of these. We're not going to go into detail on these, but if you happen to be interested in this, you could look into some advanced versions of conditional random fields yourself. And also, so that you know, in Markov models there are many different types of versions there too. Like you can have coupled hidden Markov models where you would, for example, model two modalities separately and you look at the dynamics between them. But I think that's outside the basic idea of the course. Okay, so just for definition, basically what we want to do in multimodal behavior recognition is we want to get at some label. For example, we want to separate dominant speakers from non-dominant speakers, and so our label for dominant is 0, and for non-dominant is 1, and we observe different things. They could be multimodal. In this case, we either observe speech energy, gaze, or turn taking. So these are binary observations, so they're present or not present, and these are our observations X. Or we can have a vector like this. So this is an early fusion, for example, yeah. And in generative models, we basically want to know the joint probability of X and Y together by so multiplying the prior and the likelihood. The prior is always the same in our data, so we can assess that from our data set. And the likelihood is given a label, what is the likelihood of observing this? Okay, so that's kind of like the naive Bayes idea, or the hidden Markov idea, where this becomes a sequence and this is a model. Okay? So this is what we have here, and this is in the hidden Markov model. So we have these sequences, and we have some variable states in our model. If we move on now to the discriminative model, we have a difference here. So here we have these arrows. Usually you don't have an arrow in a discriminative model, but still these are kind of some modeled together. And now what we compute is the posterior probability, which basically turns around. So here we have the likelihood where we have X given Y, and here we have Y given X. Okay? And so this turns this around, and we now compute the likelihood for a certain class, dominant or non-dominant, given an observation. Okay? And so let's go into a bit more detail of what this function here does. And basically, we'll see that this is kind of like a normalization factor. And these are our, so the normalization factor is only there so that this thing doesn't run outside of 0 to 1. And this factor here, these are our feature functions, and these are just some weights we need to learn. We define these feature functions, and the only thing that we need to learn are these weights, theta. So the difference between a linear versus a logistic model is basically just the way this separates. So in a linear model, we learn like a straight line, and in a logistic model, we learn something like this S curve, which is bounded by 0 and 1. And given we can adjust this curve, make it more steep or more flat, and that's kind of like the idea of what we are going to learn. So we're learning some sort of S-shaped or logistic function. Okay. All right. And so let's look into this. So this is our partition function, which basically just bounds this whole thing to be a probability. This is actually going to be like probably the hardest part to calculate because you have to go through all the possible combinations. And then this is our feature functions. So basically, so these feature functions, I'll have a couple of examples, but these could be anything. These are also, like in last week's paper, there are these ramps and the binary thing, that's those guys. These are the feature functions. So you have like ramps onsetting, or like you have the onset of an observation that goes down, so the evidence for this observation is valid for a certain time, but it has a decay. You have a binary observation or like a shifted one, so you have you observe an eye gaze shift, but you want to only use that later on, so you kind of keep that present in your model. And then you have these weights here in this sum. Here are some examples of feature functions, which are basically just in this case we have 6 of those because we have 2 labels and we have 3 observations, and 2 times 3 equals 6, so that k here becomes 6. And so what we have here, for example, are the following. So like feature function of yx is if yt equals 0, then we just use xt0. So that's basically if we are like assuming that this person is dominant and at a certain time, then we just use this xt, and xt0 is like speech energy, right? And xt1 is gaze, and xt2 is turn taking. So at time t, dimension this or that. Okay. And so these are our 6 feature functions, and what we need to learn is kind of these weights, which are so in this case 4 times 9, because we have like either this thing is on or off, and so this could be either 0 or 1, and these could also be like present or not present. Okay. And then for our partition function, we need to compute the sum so that basically this guy stays between 0 and 1. This is kind of complicated to compute, but it's not that important right now. So you need to kind of make sure that whatever you do here is normalized by the fact that you don't really know which state you're going to be in, or like which class is present, but you want to normalize it by all the possible classes that you have. In this case, we have 2 classes, so we would do this for 0 and for 1, so that whatever we have here is normalized by this thing. So as you can see, like this is the same thing as that, but here we assume 1, so we say yt equals 1 for this thing, so we only compute half of that, and then for down here we compute for both 0 and 1, right? And so we normalize this number by that, and then if we set this to 1 or to 0, and we normalize it again by the same number, and because we do that, that means we have also make sure that if we sum those 2 numbers up, so p of y equals 1 of given x plus p of y equals 0 given x are 1. Okay? So we keep it in between 0 and 1, but we also make sure that it's a probability, because, yeah. Is that clear? So yeah, this is just the same as here, but in this case we fix it, and in this case we just sum over all of them. Okay? Alright. And now, so this was a logistic model, and now we move on to conditional random fields, which are also taking into account, and now this becomes really complicated. Now we're taking into account that we have again a sequence of things happening. So we have our feature functions, and these are these connections here. They are lightly red, and these are the same as before, right? But also now we have these things where we can transition between dominant, non-dominant, dominant, non-dominant, dominant, and so on, right? So that now has an additional term where we basically have, again, kind of feature functions, but these are transition changes, or like transition functions, and they have again some weights associated to them. So they could be like transition probabilities from going from one class to the other. Okay? And as you can see, they have basically kind of like the same characteristics, and these are our transition matrix, or transition probabilities. So G0 of yt plus 1 is 1 if we stay in the dominant case, and this guy is 1 if we move from non-dominant to dominant, and so on. Okay? And now this whole thing also goes into the partition function. Yeah.
Does K and L can be random numbers, or it has to be the full combination of all possible transition?
K again is the number. In this case would be 6, and L is dependent on, as you can see down here, dependent on the number of states, or like the number of classes only, like not, yeah. So the transitions, so it's only 4, because we can only transition between the 2 states, or the 2 classes. Yeah, so it's 2 times 2. Okay? But we can also have different, like we could theoretically have different connections too. So these are kind of like long-range dependencies that we could model. So there's also a possibility of like increasing that K here by adding options where we can learn dependencies between a previously observed state and a currently observed variable or behavioral variable. So we can define these kinds of feature functions that could also be like t minus 5 or something like that. So that would learn like these long-range dependencies. But again, these just fall into like the different kinds of feature functions here. And also additionally, you can have different types of feature functions where you, for example, don't want to just observe the variable, but you do x squared, or the absolute value of x, or you do these ramps. So you can add various types of functions here, and like adding new feature functions to that set is valid. You can do that, and it makes it more complex to learn, but also the model becomes more powerful. For training these CRF models, we want to compute this conditional log likelihood. Log just because, why? Why do we do a log?
Probability is very small.
So that could be one reason, but also because we have an exponent in there, so if we do a log, we can just like get rid rid of that and make a sum out of it instead of a product and stuff like that. So that makes it a little easier to handle. So we have an observation sequence, we have a set of theta weights, and we want to know if the model is like 0 or 1 and so on. So given an observation sequence plus weights, we want to know what the likelihood is for a certain class. And in this case, it's a sequence of classes. Okay, and then most of the time we add a regularization parameter here. In this case, for example, we can do the L2 norm. And we could also do, so this is kind of like the Euclidean distance or the Euclidean regularization. You can do an absolute regularization, so that would be L1 norm, so instead of the 2, you write just the absolute value of theta. And what that means is, so you can see that theta is here and it's here, and this part here is only dependent on the weight. Okay? What does that mean is, so the regularization makes sure that our model only uses a certain number of the feature functions and not everything all the time. What does that mean is, we want to make sure that our model is as sparse as possible, or as powerless, or like as simple as possible, so it kind of goes into the direction of like Occam's razor. So whatever is not needed, don't use it, right? So that's like, if this penalizes the use of feature functions. And I'll show you a couple of examples like how this affects the use of the feature functions and the different types of theta variables. And you see this all the time nowadays, like in particular deep learning, where you have these huge networks that are super expressive. You always kind of need to regularize them so that they don't use everything and don't over-express, so that they don't overfit and just learn the nearest neighbor. Okay. This can be optimized through partial derivatives, and the cool thing is that it has a convex error function similar to a support vector machine. It always converges to a global minimum, so that's kind of cool. Alright, let's look at, so you don't really need to know this, but let's look at some effect of like what would happen if we use a different, So this is the important parameter here, the lambda, which is basically the multiplier for the regularization. Okay. So the regularization penalty lambda, in this case we set it to 500, and this is actually like an example that we computed. And in this case, all of the feature function variables are 0, like the weights are 0, because this is so powerful that the optimal solution is to not use any feature, because the regularization was completely overpowering the values. So now if we reduce it to 400, in this case suddenly the eye-gaze variable becomes utilized with a weight of 0.27. If we reduce it further, the pause variable also gets used. This gets increased, and in the last case, like all of them are used if we reduce this value to 50. So the less this value is, the more the features are being used, the larger the weights get. Maybe they also go down again, but so that mainly the idea is that if we change this parameter, different features are being used or not. If we go the other way, where we, for example, have a low regularization term first, and then we kind of like increase that regularization parameter, you see also that these features go away at the end. And so this is in the case of L1 norm, which is basically just the absolute value. this is just like an example algorithm on finding out like which is the most important feature. So you can basically use these CRF models to identify which features are the most powerful to detect a certain behavior. Okay. If we want to go into the direction of like building these or making these models capable of modeling, for example, hidden states as well, like the hidden Markov model. So in the CRF case, everything is observable, and we would then kind of model these CRFs with a hidden layer in between, and this hidden layer in between kind of already it gives an idea of like how you would expand these models and make them more complex. So these hidden layers in most recent work become like neural networks and really highly expressive like latent variables. So this is an example of the latent dynamic CRF, which has these hidden states that are being modeled. And this kind of looks like this, where we have, again, our dominant, non-dominant variables being observed, but then we have hidden states, and we, for example, have, in this case, 6 hidden states. We assign 3 to the dominant class and 3 to the non-dominant class, and basically these probabilities are 1 if we are for in 1, 2, 3 for y equals 0, and these are 1 for 4, 5, 6 if for y equals 1 or for y equals non-dominant. So what we need to compute now is basically this sum here, where we only model this sum for the hidden states for one class at a time, and this function here is now again the same as for the CRF, but over all the hidden states. So this is just kind of like an additional complexity. So this becomes a bit more like you can move in these states or not at any given time. Well, what that does in the end, is basically that these models become more expressive. They can model these hidden dynamics, but also that also means that that they are in the end not like you can't find a global solution anymore for these models. Okay, and just to sum up, there are, so for example, we have like the conditional random field, which can be used for segmentation and classification. There are no hidden dynamics or substructures. We have a convex error function. We have the LBCRF, the latent dynamic conditional random fields, can also be used for segmentation and classification. They do have hidden dynamics and substructure. However, that also means that they're not convex anymore. There are different initializations that are possible. And then there's also the HCRF, the hidden conditional random field, where you basically model a constant variable or like a constant class with hidden dynamics. But you can't use this anymore for segmentation because this is static. So it's for one sequence you have one class. While here you can change the class over time, or here you can also change the class over time. But in this case, you basically get a sequence, and you want to know what is the most likely class that produced this sequence, but you can't change the label within that segment. It does have hidden dynamics, which makes it a bit more powerful for classification than this, for example, but it also doesn't allow you to have a convex error function. All right, so that's that. Other questions?
Can you again tell a little difference between L1 and L2 regularization? I'm not very clear about it.
So it's just it's basically a different measure of like the sum of the weights of the weights that are used in the model. In one case you have the root of the squares, and in the other case you just have the sum of the absolute values. So that's the main difference. They have a few different properties. I think the L2 is a bit more smooth, but really, like the L1 though brings these values faster down to 0. So like the regularization parameter has more weight or more influence on the value, but it's really like not very important. Most of the time, I guess, like people use L2 regularization. I had a slide on this, but it's not really that important. Okay. Right, so we are going to have a guest lecture on Wednesday. So there's no discussion on Wednesday. I'll post the papers for Monday today, and maybe some questions as well. And yeah, so the discussion will be on Monday. We're going back to the pre-verse rhythm. All right.